start. Separation techniques, right? Let's quickly review the ones we've already discussed, right? So we've talked about magnetic separation. So this is the ability to separate magnetic components from a solid mixture, right? We might do this with, for example, car parts in a recycling construction yard. Question? You've got a? Yes?
Sometimes if you're like in a good spot or and you're lucky, if you get a magnet and you drag it around your bed, sometimes you get a magnetic. Wow.
Yeah. Right. So we can extract magnetic components by using magnets in the earth. And this is a little bit how metal detectors work. I'm not entirely sure, but my understanding is that it's looking in particular for disruptions in the magnetic field that metals particularly have. I could be wrong, right? But it's looking for some changes and it will elicit metallic responses. Okay, gravity separation and decantation. This is for our suspensions. Yes, so remember we've got an insoluble. These are all insoluble methods of separation. The suspension often will sediment. It will fall to the bottom, in which we can then decant the liquid from the top, leaving the sediment behind. We can, for example, we've got this density column that you can make at home. The little Easter egg there shows you how to make that at home using oil, sugar, colors, all sorts of things. So density column, yeah. So relative densities and immiscible layers. Immiscible, we use that term to describe liquids that won't dissolve in one another. Separating cream from milk is one example. Yes, so natural milk from a cow, yeah, is not homogenized. Homo means the same. So homogenize means for the solution to all be the same. The fatty part of the milk will separate naturally because fat, right, is insoluble in water. So there's a watery, the whey part of milk. We can separate the fat and the milk solids that are actually dispersed through the milk when we shake it and distribute it. So in our supermarkets, we have homogenized milk. That's a process by which the fat has been distributed throughout the milk. We spoke about indigenous practices. Yandying is that gravity separation. By moving our yandy, right, we can separate chaff from wheat. So the grain, the wheat grain is the good bit and the chaff is the bad bit. The chaff, right, so here's another indigenous practice called winnowing. The chaff is the bit we don't want. That's the husk that sits around the wheat grain. It's the wheat grain itself that we ground into flour. We spoke about sieving. So this is when I've got a solid substance in a liquid. It's a kind of like filter or a sieve metal mesh, right? The liquid goes through, leaving the solid component behind. You can use sieving to separate soil or dirt from rock, as an example. Spoke about filtering, and we did the prac last week of our different types of folds that correspond to a time or a rate of filtering. And hopefully what we identified was when I did the conical fold, it took a lot longer. When I did the fluted fold, the back and forth, it filtered much more effectively because we're increasing the surface area to which the liquid can go through. remember we had a mixture of salt and sand. This salt actually goes through the filter. So the remaining filtrate from that process would have still been salty. And then we use another technique we're going to talk about today, evaporation and crystallization, to get the salt out of the water. We spoke about centrifugation. And our example of that is blood, separating the components within blood. We spin it really quickly, and this is similar to density in that the different dense components separate out. We spoke about the process in which how we select a separation technique, and much of it has to do with the properties of the substance we're looking at. If it's insoluble, we're going to look at one of the 5 techniques that we just reviewed. If it's soluble, we're going to look at one of the 3 techniques we're going to discuss today. All right, so on to today. Our 3 separation techniques for soluble substances will be chromatography, evaporation, and distillation. Let's go through this. Chromatography. Chroma means color. Graphos, right, means it's not quite measure, but right, so it's relating to color. Now, some chromatography deals with colorless solutions, but often chromatography deals with colored solutions. When I've got a mixture of soluble substances, I can use something like paper. So if we look at this example, I've got different colored inks. Ink is a mixture of different dyes. And if I put that into a solution, say ethanol or water, it will separate out the components in that mixture. So the substances that are more attracted to that soluble component will rise up further along the chromatography paper. Those that are less soluble will be more attracted to the paper. And we see these different bands of color appearing for our different colored inks in this example. This is often used in chemistry, and there's more complicated versions of chromatography which we can use, right? And it's part of our year 11 and 12 chemistry study design. Two main examples in which we use this is in food chemistry. We can use chromatography to determine the quality of food and drinks. If food has been spiked or drinks have been spiked, we can use chromatography to determine that. Also often use it in forensic science. So we can look at blood, separate it out in different ways, right? Or it can be identifying components of drugs in people's blood or urine. Because if we match that against a pure sample of the drug, the bands that separate will be equal for that component. Two, distillation. So a couple of nights ago, I had a whiskey, and a whiskey is produced in a distillery. So whiskies actually start off as a beer. Beer and wine, for example, right, are naturally produced. The amount of alcohol in beer and wine is naturally produced as a result of yeast. Yeast ferments sugar in either the juice from a grape or producing alcohol from the sugar, from the malt, from the barley, or the wheat in which we're adding for a beer. But there's a limitation. So yeast only produces a maximum of 10 to 14% of alcohol. Something like a whiskey can be over 50% alcohol, right? And so what happens with a distillery is it takes that beer and ethanol, which is the alcohol in alcoholic drinks, it has a lower boiling point than water, right? So it's going to vaporize off first. So we can extract the alcohol from that and collect it off. And then for a whiskey, we take that extracted ethanol that's got other little components in it that are also volatile and that have evaporated off from the beer. And we take that and we put it into a barrel. Why a barrel? It's really interesting. So the barrel adds characteristics. So the wood and stuff, some of the soluble components within the wood add to the characteristics of the whiskey. And then we leave it in there for at least 8 years. It's a long time, right? So some of the whiskies I have at home have been left in barrels for 15 years. And the thought is, the older it's left in the barrel, the differences in flavors that you'll get. So often a whiskey will be distilled, placed into a barrel that was previously used for wine or previously used for sherry or port. And so it's getting different characteristic flavors and smells from that barrel. So that's a practical application for distilling. We've got this idea, so there I wanted to include some Indigenous knowledge, but I also wanted to ensure that it had some scientific benefit too. We've got this thing called an aeromophila in Australia. Aeromophila, it's Latin. It's the Latin name for this flower. Get the laser pointer. Right, this flower here, the Australian native species, it's called an aeromophila. And often it's tea tree, right? Tea tree is one example of aeromophila. And aeromophila contains these, a number of these components here. Now, I'm not expecting you to know this. I'm sharing this with you for your appreciation. So in Central Australia, they use this steam distillation process. So they took wet aeromophila leaves, placed it onto fires, and some of this is cultural practices with smoke ceremonies, and the vapors from that contain these components. And these components of the aeromophila plant have been shown to be antifungal and antibacterial. And so as part of that smoking ceremony, this process of smoking these wet leaves of aeromophila plants, they would often do that to people that were sick and suffering from respiratory illnesses. They would inhale these and it reduces the microbes within the respiratory system. So appreciate for a moment, we've got thousands of years of Indigenous practice that actually leads to something that's real, something that's meaningful. Lastly, evaporation. And this is what we were doing in our prac yesterday. It's not, it's salt. I'll talk about that in a moment. So evaporation, to vaporize. So this is particularly for soluble components, where the soluble component has a much higher boiling point than water. So what we're actually doing is we're boiling off the water in order to leave the salt behind. Evaporation and salt has been around for millennia. And this is a salt production farm. So what they do is they create these channels where they're collecting water off, say, oceans and large lakes. Water will go down these channels, and then they will spread the water onto really thin onto these parts of land. The water will naturally vaporize off, leaving the salt, and then they will collect the salt and sell that off. So salt harvesting has been done for millennia. And some salt, you'll notice, is pink. And pink is because of a natural bacterium within the water that gives that pink characteristic color. Linking this idea of slow and fast vaporization, which is what our prac was about. And what I wanted to show you, I'm going to pass these around. The slow evaporation hasn't finished, but I don't know if you can see this clearly. So this is a sample of slow vaporization. Hopefully you can compare that with your fast. The one thing I want you to notice is the fast evaporation leads to really small crystal size. The slow vaporization leads to much larger crystal size because that smaller differences in temperature allow the time for the crystals to grow. Yeah, whereas we don't have that in fast vaporization. There's an example to show you that. A would be a fast vaporization. B is a slow vaporization. We can see the difference in the crystal size. Depends what you want. So if we're wanting to naturally produce some minerals or crystals, we may want them to be larger for appearance sake. If we're simply producing, wanting to vaporize salt, we may want to do that quickly for industrial and commercial benefit. It's still the same material, just its physical form is different. Okay, so to recap, we've spoken about all of those separation techniques. We've spoken about the process by which we select an appropriate technique. And today we've looked at chromatography, distillation, and evaporation.